Hello everyone, welcome. What we are going to do today is we already discussed what is unit load method and how the unit load method can be applied to truss. Now we are going to demonstrate that through some examples. Okay. The example that we'll be doing is to take this example. It is a statically determinate truss, and what we need to find out is deflection at joint C. And the axial rigidity A is same for all members. So, all the dimensions and loads are given. Okay. So, let us start the analysis. So, the truss is like this. This is and then this is member A, this is member A, this is member B, member B, then C, then D, and then we have horizontal load of P at C and then a vertical load 2P at D. Okay. And this is roller support, this is hinge support, and this is roller support here. Okay. Now, the first step in unit load method is first we need to analyze the structure as we need to determine the forces in all the members, then apply unit load in the same structure, remove all the loads and apply the unit load in the direction at the point where we want to find out the displacement, and also the load should be in the direction in which we want to find out the displacement, and then those two results we need to use those two results to get the final displacement. Okay. Now, let us first analyze this, draw the free body diagram of this member, the entire structure. The free body diagram will be, we have this will be the horizontal reaction at AX, okay, and this will be the horizontal reaction BX, and then vertical reaction BY, Now, if we apply the equilibrium equation, let summation of Fy is equal to 0, the forces we have in Fy direction in 2P and By, we have By is equal to this will give us By is equal to 2P. Okay. And then we can take summation of moment about A is equal to 0, summation of moment about A. Again, please remember, when you draw the free body diagram, then the structure needs to be free from the support, and that support needs to be represented by the forces. So, when you actually draw it, if you are showing these reactions here, so don't show these supports. I am showing it because then I don't have to draw the same figure once again. Okay. Now, let us summation of moment about A is equal to 0, that the moment will be we have the contribution will be from 2P, which is clockwise, and then P, which is clockwise, and then contribution from Bx, which is again clockwise, and as per our sign convention, clockwise is positive. So, what we have is this will give us P into this distance is 3 meter, this distance is 4 meter. So, 2P into 3 plus P into 4 plus By into 4, this is equal to 0, and this will give us By is equal to minus 5 by 2 P. So, this is By. Okay. Now, then next what we can do is we take summation of, we have used summation of Fy is equal to 0, moment about A is equal to 0, take another equilibrium condition, summation of Fx is equal to 0, and this will give us Ax is equal to the forces we have in x direction is only Bx and Bx, P and Ax, their sum will be 0, and we will get Ax is equal to 3 P by 2. So, this is the reaction, all these reactions. Okay. So, once we have this reaction, we need to find out what are the member forces. Now, we have already discussed method of section, method of joints. We can apply any method to find out the forces in these members. But let us try to find out in before actually we use any method of section and do the calculation, just by inspection let us find out whether we can have some information about some of the members. Okay, if for instance if you take joint D, then the forces will have the member force in AD, member force is CD, which is in vertical direction, and then in vertical direction 2p. So, there is no horizontal force which can balance the horizontal force in member AD. So, naturally the force in this member will be 0. So, this is a 0 force member AD is a 0 force member. Okay. Now, if the member AD is 0 force member, then if we take joint D, then the free body diagram of joint D will be FBD of D. If we take, then this will be the force in this direction, which is 2p, and then this force in member CD, FCD, and naturally from this we can say that FCD is equal to 2p. So, to say FCD is equal to 2p, really you don't have to do this, but just looking, we are actually applying the equilibrium condition, but you don't have to write and see and write and take the components of forces in y direction and find out FCD is equal to 2p. Just by looking at it, we can say that FCD will be 2p. So, FCD is equal to, in this member, FCD is equal to 2p. Okay. So, FCD is equal to 2p. Great. Okay, let us write it here. So, the force in this member is 2p. So, force in this member is 2p. Okay. Now, then once this is done, so this is a 0 force member, and then again we can take free body diagram of joint B. If we take free body diagram of joint B, then what are the forces we have? FBD of joint B, then we have member force BC, FBC, then member force BA. If you remember, that is our sign convention. We assume tension in member is positive, FBA, and then BX, and then BY. Bx and By already we have determined. Then we need to apply the equilibrium equation on this summation of Fx and summation of Fy is equal to 0. Then if we do that, summation of Fx is equal to 0, this will give us Fbc is equal to minus Bx. And now Bx is equal to, already we have determined, this is Bx, this is Bx, this is Bx. This is Bx, this is Bx. If Bx is equal to minus 2.5, so Fbc will be 2.5 p. So, this is force in member BC. Similarly, if we take summation of Fy is equal to 0, then this will give us Fba will be By is equal to 2p, already we have obtained. So, this is 2p. So, this force is BC is 2.5 p, 2.5 p, and in BA it is 2p, it is 2p here. So, only thing left is member AC, the force in member AC, that we can determine by taking free body diagram of either joint A or joint C. If we take free body diagram of joint A, the forces will be, so FBD of A, we have there is the reaction force AX, and then FBC, which we have already determined, and then this force is FCD. There is force FAD also, but since FAD is a 0 force member, we are not showing it explicitly. And AX, the value of AX is already obtained, value of FBC is already obtained, and we know this angle because this is 4 meter, this is 3 meter. If we apply the equilibrium condition, we get FAC is equal to FAC, this is FAC, this is FCA or AC, FCA will get minus 2.5 P, minus 2.5 P. So, this is the reactions. Okay. So, now what we have? We have the forces in all the members because of the external load. Now, next what we need to do is unit load method. We take the same structure and apply unit load at a point where we want to find the displacement, and also the load has to be applied in the direction of the displacement. Okay. Now, so what we can do is we take the same structure once again and apply. First we apply the unit load. So, take the same structure, this is hinge, this is roller A, B, C, D, and then we have a diagonal member AC. Now, first let us find out the horizontal displacement of C. If we want to find out the horizontal displacement at C, then this will be 1. Okay. We need to apply unit load in this direction. And now, because of this unit load, what are the forces in the members that we need to determine? Again, without doing any calculation, just by looking at this structure, we can find out the forces. For instance, if we see the free body diagram of this joint, there is only forces will be the member force in AD and member force in CD, which are horizontal and vertical respectively. There is no other horizontal and vertical loads to balance them. So, we can say that these force and these force, they are all 0 force member. Okay. Now, since you look at joint C we have horizontal load of 1 Newton, horizontal load of 1, and then there will be horizontal load which is the member force in BC. There is no and then member force in CA. Now, member force in the force in member CA has horizontal and vertical component, but there is no other vertical load which can balance the vertical component of member CA. So, therefore, the force in member CA has to be equal to 0, right. Now, if the force in member CA is equal to 0, look at joint A, reaction in joint A will be in horizontal direction because it is roller support, and then joint A only vertical force we have, the member force in BA, but force in this member and force in this member, they are 0. So, there is no other vertical force which can balance the member force in AB. So, naturally this also has to be a 0 force member. Now, if this is a 0 force member, now look at joint C. If you look at joint C, then forces in the member will be CB and all other forces at 0. And then what would be the force in member CB? Force in member CB will be 1. Okay. Now, so you see, without actually doing any calculation, we should be able to find out for such small structure, if we can identify 0 force member by looking at this structure, then our problems becomes easier. Now, this will give you the forces in now this we require to determine force in horizontal direction. Now, we also need to find out force in vertical direction, and for that take the same structure once again, and this is roller, this is hinge, and then this is A, B, C and D. Then we need to apply a force unit load in vertical direction. Okay. Now, let us find out the forces in the member. For the same reason, here the force in member CD and force in member AD will be 0. Okay. Now, then again we need to find out, we can do the similar exercise, any method of joints or method of sections to determine the forces in other members. And if you do that, the final forces in member will be, this member will be 1.25, this will be minus 3.4 minus 3 by 4. And this member force will be minus 1. Okay. We know how to determine this. Okay. Now, so this will give us horizontal displacement and this will give us vertical displacement. Now, let us write the everything in a tabular form. So, take a column for member, okay, then column for the forces in member due to the externally applied load, then member in this force in here, and then the another column for this, and then we need a column for length, and then we need column for okay, let us write it. This is member. This is member, okay, and this is N. What is N? N is the member forces. These are the member forces because of due to the external load on the structure, okay. And then we have N1. N1 is what? N1 is the force in this direction due to the horizontal load due to the unit load at C in horizontal direction. And then N2, which is the forces in this these N2 are the member forces due to the horizontal due to unit load at C in vertical direction, okay. And then this is the length of each member, okay, and then this is N1 N L and this is N2 N L. So, this is this will give us this displacement and this will give us this displacement, okay. Now, so let us write all the members. So, we have total 5 members here. So, 1, 2, 3, 4 and then 5, So, this is member AB and then BC, CD and then AD and finally, the diagonal member AC. Okay. Now, let us see what are the forces we have. The force in member, if you can see this, the member forces in AB it is 2p. So, this is 2p and in BC it is 2.5p, and then CD it is 2p. This member is a 0 force member, it is 0, and then this member it is minus 2.5. We have already determined it. So, it is minus 2.5 p. So, this value is minus 2.5 p. So, these are the forces in the member due to the external load. Now, what is N1? N1 is only BC is 1 and all other are 0. So, this is 0, this is 1, 0, 0, 0, and similarly N2 AD and CD are 0. So, AD this is 0 and this is 0, and then member AB is minus 1, and then member BC is minus 3/4, and then finally member AC is 1.25. Lengths are this is 4 meter, and then this is 3, then 4 meter, 3 meter, and this length will be 5 meter. Okay. Then what is N1L? These all will be 0. This is 0, this is 0, this is 0, this is 0, and this will become 3 into 2.5 p into 1 into 3, 7.5 p. Okay. And similarly, in this case N into capital N into minus capital N into N2 into L. So, these become minus 8 p, and then this becomes 2.5 into minus 3/4 into 3. This is minus 5.625, and this becomes 0, this is 0, and this become minus 2.5 into 1.25 into 5, this is minus 15.625 p. Okay. These are all p. So, this is p. Now, what is delta? If we remember, so delta C delta C1 will be means it is the displacement at C in this is suppose this is direction 1 and this is direction 2. Okay. So, delta C1 is the displacement at C in direction 1. In direction 1 will be summation of, we know that it is summation of n1 L divided by A. Okay. Now, A is constant for all the members, this is axial rigidity, and n1 L, this is the n and the summation of this column. So, this becomes, so this gives us delta C1 is equal to 7.5 P by A. So, this is the displacement in displacement at C in direction 1. Similarly, if we did displacement at C in direction 2 will be summation of n2 L by AE. Okay. Now, n into L are already obtained. This is the summation of all the summation of the entire column, and if you sum them, then this becomes minus. So, these become delta C2 is equal to minus 29 point, if you sum them out, 29.25 by AE. So, what it says that delta the point C, this is our direction, this is our positive direction 1 and positive direction 2. So, this is positive, it means that in direction 1 the force will be in the displacement will be in the direction of unit load, and we applied unit load in this direction. So, displacement will be in this direction, but delta C is negative, means the displacement will be in the direction opposite to the unit load. Now, we applied unit load in this direction, upward direction, but since it is negative, displacement will be in the opposite direction. Opposite direction means displacement will be in this direction. Okay. So, now similar procedure we can apply to find out displacement at any point. Okay. The n will remain same, this column will remain same for this structure. Only thing is n1 into these forces in the member due to the unit load will only change. So, wherever if we want to find out displacement at point D, similar way we need to apply unit load at point D in the direction in which we want to determine the displacements. Okay. So, this is how we can apply unit load method to find out displacement at any particular joint in truss. Okay. Now, the same truss, if we want to see the deflected profile, you see that this is the deflected profile of the truss. Now, as I said, this member as per our calculation, the displacement member C, horizontal displacement will be in this direction and the vertical displacement will be downward direction, and that is what it is happening here. And another thing is there which is very obvious, you see the horizontal displacement is smaller as compared to the vertical displacement, which you also have observed. Okay. So, this is how the member. Now, another thing you see the point B here, since it is hinge support, it cannot move in any direction, either horizontal or vertical direction, whereas joint A is roller support. So, this joint A cannot move in this direction, because that is the direction the movement in the translation in this direction is constrained, but joint A is free to move in vertical direction. That is what is happening here. This is the figure that the animation that you can see, it is a scaled deformation. So, actual deformation is not that much in this structure, but it is just to have a proper view of the deformed shape, it is scaled. Okay. So, that is how we can apply unit load method in truss. We will discuss more on the principle of virtual work and its application to different structures. Okay, but for as far as today's class is concerned, we stop here. See you in the next class. Thank you.